Yeah. All right. Good afternoon, everyone, and thanks for coming. We hope you enjoyed your coffee break so far. Today we're going to talk about the Swift deployment at Turkcell. Personally, I'm working on Swift for some time now, and mostly upstream. But I also have some DevOps background from my work before that. And so in 2014, Turkcell reached out to me, or to Red Hat especially, and to discuss Swift and some Swift deployments. That said, today with me are Orhan and Doruk. Please introduce yourself.
Hello everyone, my name is Orhan Bıyıklıoğlu. I am working as a senior systems administrator for Turkcell for more than 10 years now.
Hi, my name is Doruk Aksoy. I'm also working with Turkcell nearly 5 years and responsible for the Openstack environment operations.
All right. So before we're going to talk about Swift itself, we're going to have a short introduction to Turkcell and what Turkcell is doing. And yeah, I will tell you a little bit about it.
Thank you, Christian. I will try to give a short introduction about Turkcell, who we are and what we are doing. Turkcell has actually been known as the leading mobile operator in Turkey and in the region. But currently we are defining ourselves as a converged telecommunication and technology services provider. And we had been founded and headquartered in Turkey, but we have group companies in 9 countries. And in these 9 countries, we are providing our clients voice, data, television, and value-added services on both mobile and fixed networks. Currently, we are serving more than 66 million customers in these 9 countries. And by the way, Turkcell is also has been listed on New York Stock Exchange and Borsa Istanbul since year 2000, and is the only New York Stock Exchange listed company in Turkey. Sorry, too fast. As a technology services provider, we are also providing cloud and data center services to our customers as well. In June this year, we have opened Turkey's largest data center, actually in Gebze near Istanbul. We are planning to provide all kinds of cloud services in this data center to our clients. Also, we would like to serve global internet companies as well as the Turkish public and private sector companies. This data center is a state-of-the-art Tier 3 certified data center. It's spread over an area of 33,000 square meters, and it has a white space area of 10,000 square meters. We are also building a similar data center in Ankara, which we will be using as our disaster recovery center, and also will provide the same services there to our clients. As part of our cloud services initiative, we have created the product called Lifebox, which Lifebox is a public cloud storage offering for the end user, where you can store and share photos, videos, and all kind of documents. The product actually has been called Akıllı Depo, which is the Turkish name for smart storage. But we have recently rebranded it as Lifebox because of our global initiatives and because of our operations in the other countries. It's now called Lifebox. The product can be reached at mylifebox.com, and it can also be used on mobile devices as well. We have client apps for iOS or Android devices on the app stores, where you can get the app and start using our product. As you know, there are many different public cloud storage offerings out there. So the question is, what was the motivation for Turkcell to build such a service? As I've stated, we are currently serving more than 66 million clients already, and a great majority of these clients are mobile users. And a large number of these mobile users are actually using smartphones. Since smartphones are one of the primary reasons why people are producing so much data nowadays, people need some sort of some cloud storage space to store their extra data, because as you know, the capacity of our devices is never enough. We are taking too much pictures, shooting videos, producing a huge amount of data, and our clients were always complaining about the capacity of their devices. As the network operator and also as the cloud services provider, which is the closest to our clients, we wanted to provide them our own solution where they can use easily, and we also wanted to provide them a solution at very competitive prices. It's the very competitive prices. We are all right. Let me explain about how we started this project and how we implemented the solution. Actually, we started this project in year 2014, and back then we implemented a solution from one of our vendors. It was a legacy integrated solution. This solution consisted of large enterprise storage boxes and a gateway application in between, which acts as a gateway between the storage devices and the clients. After a short while, we decided to implement our own solution using Openstack Swift. In 2015, we decided to implement the solution using Openstack Swift, but back then we had no previous experience with Openstack or Swift, so we decided to get some consulting from our vendor Red Hat. That's when Christian came into picture. He has been our Swift consultant since then. With his support, we have designed and implemented our solution from scratch within a couple of months and put it in production. He not only helped to design and build our infrastructure, but he also helped he also given guidance to our developers how we can actually implement the application using the Swift APIs. Currently, our product Lifebox is actually running on Openstack Swift, and it has over 3.3 petabytes of storage, and we have more than 3 million users. Actually, while migrating from the legacy solution to the Openstack Swift, we did something different, and we wanted to keep our existing investment in those enterprise storage boxes and actually use those enterprise storage boxes as the backend disks in our Swift environment. I think Christian and Doruk will tell more about this, but this is one of the differentiating factors of our Swift implementation. Okay, now I would like to give a short insight about the look and feel of the product. Here you can see the screenshots of our mobile client. Using this client, you can browse, upload, download, and your pictures, videos, etc. And it has a decent UI, and also we have this is the screenshots for the desktop version which you can access via browser and use pretty much the same features. All right, if we return back to OpenStack, as I mentioned, we have built our solution using OpenStack Swift, OpenStack, but OpenStack is a very big framework of very large ecosystem, and there are many different components. For this project, we have specifically used Swift and Keystone, and that was enough for our project. Now, I would like to let Christian explain how we use Swift to create our product.
Yeah, thanks, Orhan. All right, so planning the Swift deployment. As Orhan said, I came into play at the end of 2014, and at that stage there was a previous solution already in place, so we had to find a solution to make the migration as smooth as possible while being in production, and so we had some discussions around this. So first, let's have a short look why Swift is actually a good use case in this case, or is a good fit. What we're storing is unstructured data, right? Your clients don't care about where you store the data. They don't need a POSIX file system, for example, and logging and all these mechanisms that come with it. They just need, for example, an URL where they can access the data. If you're accessing the application on the mobile phone and you're viewing an image or a photo, you just use URL at the end of the day. So all the metadata that is attached, for example, to a photo, the name of it, where it has been recorded, who you share the photo or video with, is actually stored separately, not inside Swift itself. It's stored in a database as well as an Elasticsearch for, well, searching. And that makes it actually quite easy to implement this. So Swift itself is, I think, well known for its availability, for its durability, scalability, but it's also a very good case, a good fit in this case because of its flexibility. As Orhan said before, there was a storage system in place already. So there were quite a bunch of servers existing, quite a bunch of disks that were already paid for. So we wanted to reuse them actually. Another case or another important thing that why Swift is a good fit is a failure resiliency. So as an operator of a large deployment like this, you don't want to tell your customers we're down for the next 4 hours or something like that. Your users are using the application all the time, 24/7 basically, and you try to minimize the downtime as far as possible. And last but not least, it was very important to run some customized middleware on Swift itself. So we're going to have a look into that shortly, but some of the actual part of the application is running inside the Swift proxy itself. So this made it much easier because we need less servers actually to run the application, because all the data can be, for example, modified inside the proxy when it's uploaded by the users. And as Orhan said, we are not running a complete Openstack cloud, including Nova and Celometer, for example, or Neutron. We're just running Openstack Swift together with Keystone for authentication services. So when you talk about developing applications on top of OpenStack Swift, you need to keep a few things in mind. Actually, you want to distribute your objects and your containers as far as possible. It's probably not a very good idea to have a single account and to have a single container within Swift and store billions of objects from every user into this container, at least not today. We have a few people working on that. One of them is sitting there right next to him, there. And, but right now it's a good idea to actually distribute it. You also have to keep in mind that Swift is an eventually consistent system. That means, for example, when you upload a new object to Swift and you have an outage on some part of your cluster, that maybe your container listing is not showing this new object right after the upload. Because we keep a separate layer of database and Elasticsearch separated from Swift, that was no problem in this case. So when we planned the deployment, actually, we needed to estimate our growth, actually, and need to choose our partition power wisely. So the partition power is a setting within Swift that is responsible for, basically for the distribution of the data inside your cluster. If you want to get a few more details about that, there will be another talk tomorrow afternoon where we are going to talk about this. But basically, it's a fixed value, and it's very important to select a value that is neither too small nor too big, because otherwise you run into problems later on. And last but not least, you need to know your failure domains. So a failure domain might be, for example, on the smallest level, a single server, on a little bit bigger level, a rack, for example, or finally a whole data center. So when you take these into account, you can build a cluster that can even tolerate failing a complete data center, for example, in case you have 2 data centers, of course. All right, let's talk a little bit about the architecture. So when a user is using the application, the mobile phone application or the desktop application, the user uploads a new file, a new video or photo, it gets sent to the Swift proxy. And the Swift proxy itself talks to Keystone, checks authentication, Keystone itself is talking to MySQL database, and so on and so forth. What happens afterwards, after the upload of this video, for example, has been successfully, there's an event triggered directly from the Swift proxy using a custom middleware, and it's sent to RabbitMQ. So RabbitMQ is a message queuing system, and then it gets processed afterwards. So we have 3 actions. So whenever you upload a new object, you create, or the system creates actually an entry in the Oracle database. It creates another entry in the Elasticsearch cluster, and it also triggers the creation of previews, for example, using ImageMagick and FFmpeg. So all of this is done asynchronously outside of the Swift cluster itself, but of course the data that is generated here, for example the thumbnail, is sent back to the Swift proxy, and using the Swift proxy to store it actually replicated across the cluster. Now, when a user finally goes to the application and browses his files or searches for something, it is directly talking to the application part and to the Oracle database and Elasticsearch and retrieving back URLs, and these URLs are actually authenticated URLs that you are using to access the data on Swift. All right, so Doruk is working on the operations team, and he will tell you a little bit about, well, actually the deployment.
Thanks. I mentioned it before, I'm responsible for the Turkcell Openstack operations nearly for 3 years. Let's have a look a little deep inside the infrastructure design of our project. At the beginning, we started using only 8 physical servers. On the beginning of the project, there were 3 existing storage systems, and we assigned 13 LUNs, each LUN size of 4 terabytes to each server. So every region has nearly 150 terabyte data disks. Rings are using 3 regions, 1 per storage system. Every region has its own storage box. Best practice says Swift has to have 3 replicas, so we made it like this. Our region 1 and region 2 is in Istanbul data centers, and region 3 is the Ankara data center. One storage system with 2 servers are located in the remote data center Ankara. So initially we used write affinity to write only region 1 and region 2. So we expect Swift should move 1 replica to Ankara afterwards. But after that, when we're growing, the things are changed. We need more capacity. Then we change some things in the infrastructure design like this. We start using dedicated firewalls and dedicated load balancers because of high bandwidth. Servers are classic rack mount servers with 2 sockets from different vendors. The CPUs are version 3 and version 4 Intel Xeons. Let's take a look a little bit network part. We have 2 VLANs. One VLAN for DMZ and for all connections, and 1 private VLAN for only synchronization, the rsync, Swift rsync data. We have 4 10 gigabit network interfaces for each server. Also, we use bonding configuration for high availability. After some time, we make also upgrades in our storage systems because of capacity needed. With that, we add more servers to our cluster. After that, we started with 8 servers, but now we have 33 servers for all regions, 11 for each region. Each server now have nearly 25 LUNs. The capacity is a capacity of 4 terabytes. So we can say that every server has a 100 terabyte data disks. So when you look at the cluster, All regions have 1.1 petabyte data disks. For all cluster, we have 3.3 petabyte disk for Swift cluster. Okay, let's have a look closer at one node. These were existing servers, so each node runs all services. We have account servers, container, and object, also with proxy and the keystone. Proxies also run a few middlewares that we develop in-house, sending notification to RabbitMQ, and checking if required headers are sent along. You see, there is a MySQL. We have we have two MySQL servers working as a cluster, active, passive. So finally, when you see whole the picture, we can say that nearly we are a 99% high available cluster system. Okay, deploying Swift, yeah. In our environment, yeah, we have a big enterprise environment. When we install operating system using our automatic provisioning tools. After that, we install Openstack packets from Red Hat repos to servers, configure all parameters, system, network, disks, file systems, Keystone, Swift, everything. Then adding new servers to Ring and copy the fresh Ring files to all servers. After that, we finally start the rebalance process. But you have to be careful about rebalancing. If you add too much new servers to the cluster at the same time, Swift try to copy the data to new server so quickly. So it's a normal habit for this, but it's good for capacity, and your percentage will decrease. But the problem is the existing production servers. The existing Swift try to copy big data to empty servers as quick as it can. For example, if trend of one production server load nearly 20 or 30%, when you start the rebalance with so much disks or with new servers, the trend will increase nearly 60 and 70%. So it will be a problem for production environment and also for our customers. But now we have that know-how how much data we have to increase at what time, so we can handle it. After rebalancing, we just monitoring the system. Okay, I told you before we install and configure everything with manually. Ansible, we can talk about Ansible. Ansible is a great tool to manage big environments. Before Ansible, installing servers, packages, configuring, tuning, everything we made it manually. Also, in the rebalance process, we copied the Swift files, Ring files, and the other configuration items needed with rsyncs or SCP manually. After Ansible, now everything is more clear and reliable. Just you have to be careful about get the Ansible files, libraries, and playbook up to date. So adding servers or disk switch is much easier now. Let's have a look at the monitoring part. Yeah, we separate info and warn logs files for each services, you know, Keystone, object, account, and other things. Stats metric collected and visualized using Grafana. I will show you a screenshot about Grafana and tell you after that. And Swift Recon to collect important metrics and trigger alarms for whole cluster. Swift dispersion report, it's very important after rebalancing to show what's going on in our environment. And we have some health check middlewares queried by existing monitoring systems. Yeah, this is our Grafana screenshot. You can find lots of information about cluster I mean, whatever you want, you can put in here. For example, now you see in the free space of cluster, lowest disk, one loon in the cluster, highest minimum 1 minute load, incoming data transfer, request per second, I/O waits, and at the bottom is the CPU loads of the whole nodes. I told you before, Swift dispersion report. Dispersion stores test objects distributed across the cluster. All replicas are queried by the tool. Some replicas will be transferred after a rebalance and therefore not available. So your rate will vary between 66% and 100% if only max one replica is missing. And lastly, querying metrics directly from Swift, querying objects with our internal web services, and lastly, Swift recon replication command let us know the metrics about replication and what going on. Now I will give you words, Chris, again.
All right.
To take challenge.
Thanks, Dork.
Yeah.
So when you operate a Swift cluster at that scale, especially with a few million users and hundreds of thousands of users using it every day, you will run into some challenges. As Dork said, we increased the size of the cluster quite a bit in the meantime, much earlier than we expected, which is actually good. This is nice as an operator and as a company. But we had to actually find a few workarounds. So initially we started with 8 servers, 6 actually in Istanbul, 2 in Ankara site, as Dork said. And we had to add 5 new servers very quickly. Well, actually, if you have 5 servers to 8 existing servers, you need to, well, move about 40% of the existing data to the new servers to rebalance actually the cluster, right? So you want to have some of the existing data on the new servers, and the old servers should have less storage used. We had also, as Dork said, write affinity enabled. So write affinity basically was enabled because we wanted to ensure that all data that is coming in, well, it's replicated 3 times, but all the data that is coming in is initially written to the Istanbul side. And the Ankara side is only used, well, as a last resort in case Istanbul gets lost or destroyed, for example. As you know, Istanbul is, for example, close to earthquakes. It might happen from time to time, so you want to be sure that even if something happens on that side, that you're still able to recover from that and have some data offsite. So when you enable write affinity, you write more data actually to your regions that you have in your cluster. Let's assume you have 3 replicas and you have 3 regions in our case, and you enable write affinity to only write to 2 regions initially. Actually, there are still 3 replicas written then, but these 3 replicas are written to 2 zones, to 2 regions. So that means these 2 regions, at least for some time, need to hold more data until this data is finally moved by the replicators to the 3rd region. So it requires more space, and depending on the speed of the replication process, that might pile up actually, especially if you have a lot of data coming in. So initially, our growth was very fast, and, well, it's still very fast, but we had a smaller cluster, and we could barely keep up with adding new disks and new servers. So what was very important in that case for us was to run the replicators with an option called handoffs first. So handoffs first actually moves data that is not intended to be on these primary nodes to their actually primary nodes, for example, in their 3rd region. Now, well, actually, I was talking about like replication time, and we had some troubles initially with the replication time. It took a lot of time. We are not talking about days here anymore, and so we digged into the reasons why this happened. Well, the cluster growth was very high, but actually we had also to tune, of course, the existing default settings for Swift, for example, the replicator workers. But on the one side, you need to use a value that is not too high, because otherwise it affects other services. but you also need to use a value that is, well, fits your use case and your application speed. So we had to tune a few things, but at the end of the day, this improved the situation a lot for us, but not totally. So we had a look what else is going on inside of our cluster. So one of the issues we found actually is when we looked at low-level I/O statistics. So when you store a lot of data on a file system, your system actually keeps some inode cache entries, and and the amount of inode cache entries depends on the amount of storage that you attach to each server, and depending on this size, your memory usage will go up. So what happened here is that the inode cache there were actually inode cache misses. So, for example, when you dig deep into the directory structure of Swift on the disk, on the server itself, and for example did an ls just to show which files are existing there, it took a lot of time to actually list the current directory. And of course this affects not only your ls operation but also your replication process. So we had to tune this a little bit. What helped a lot is a VFS cache pressure setting, which is by default set to 100 on Red Hat Enterprise Linux. We set it down to 1, and that actually means that the kernel is not expiring cache entries that fast. You can't set it, well, you can, but you should never set it to 0 actually, because some people are smiling there in the background. It's very likely actually that you run out of memory in this case. There were some other issues that we had in the meantime. For example, one day we got reports from users that were not able to skip parts of video files, so they wanted to view a longer video, and they wanted to skip a little bit forward a few minutes, and it started, but then it stopped suddenly. And we were like, okay, what's going on here? What is Swift doing, right, when you stream out data? Actually, it was not Swift. Good for us. We found the reason finally. It was one of the load balancers that actually had a setting that affected this video streaming, and especially when you skipped part of the data. So for us, it was very important not only to look at Swift itself when you run into some troubles, but to the global picture, taking your load balancers or SSL terminators into account as well. And other parts like keystone response times, of course, this will affect your Swift cluster as well. If keystone is too slow to actually, if it's slow, then it will slow down Swift as well. And we had to work around this as well. All right, so that's that. We had a lot of growth, and Orhan is telling us a little bit about the future of this cluster and this project.
Thank you, Christian. As Christian and Dirk mentioned, we have actually expanded our capacity during the project, and also, as I said, we currently have more than 3 million users now. The growth was actually higher than we initially expected. We already expanded our environment, but we have also plans to expand our server and storage capacity to 5 times it's now by the end of next year. Of course, this will bring the challenges that Christian mentioned. We will have to be very careful while doing this. We will need to do this over time in order to not move too much data at once. It will bring a lot of load. We are also planning to upgrade our operating system and Openstack platform releases. That's one of the items on our list as well. But of course, we will have to do this in production too, and it has its own challenges. One other thing that we are planning for now is to introduce the X-Stack into our monitoring environment, so we will do better log monitoring and analysis, which will help us as the operations guys. We are also planning to change our infrastructure a little bit. As Doruk mentioned, currently we are running all Swift and Keystone services on all servers. As our environment is growing, we are planning to separate these services and put them on their dedicated servers. We will be installing a few dedicated Keystone servers, and we will also be separating object storage nodes. We will have dedicated storage nodes. We are also planning to use storage policies to keep the data balanced on our cluster. Other than that, this was our first project with Openstack and with Swift, but we have already started a second project where we are implementing a second Swift cluster for one of our other services, one of our other applications, which is called BIP, which is an instant messaging application from Turkcell, another service. We have also plans to use other OpenStack features. Since we are a telco, we have also plans regarding NFV or other use cases for OpenStack. I think that's all from my part. We will be happy to take your questions if you have any. Otherwise, thank you very much for listening to us.
Yeah.
Any questions? Okay.
Yeah. Any questions? John has a question. I see that. Need a special introduction to Swift 101, maybe? Just kidding.
Everything is clear.
Do you open source the Android app?
If you're going to open source the Android app,
Currently, we don't have plans on that, but we'll see.
actually, well, independent of this architecture, I think it's a little bit tough because to run an application like this, you need all the infrastructure, right?
Yes.
So you would require to open up basically everything to everyone, and otherwise it will be tough to use it.
The question is because there is, as part of the OpenStack SDK, there's some rudimentary Android app that is totally out of date.
Yeah.
Yes.
So for Android developers to get hooked to Swift in some kind is really tough these days.
That's true. I think in this case it would be difficult because you're not only talking to Swift, you're also talking to a different application. And you need actually the second application, for example, to know which object to retrieve or where to send the new object to. So it's not the native, so the application, the mobile application is not talking directly native to the native Swift interface. Well, it's talking to the native interface, but it's not using it in this way. Yeah. Yeah, Matthew. Do you have a mic there? Well.
I'm not yelling.
Yeah.
No. You guys are talking. Is that working? No, hello.
It was working.
I don't think so working.
It says on.
All right, I repeat.
Is that better? No?
I repeat your question.
Oh, you repeat the question. So, you said you guys are using custom middleware.
Yes.
That obviously is a bit like what we want to do in Swift with our messaging. You want to send an update to a RabbitMQ server.
Yes.
It sounds like your cluster is quite busy. It really.
Oh, yes.
So, did you have any problems with, say, the RabbitMQ message bus, or what happens if you miss a message? Like, what happens to that image?
So.
That doesn't get updated. There's no thumbnails.
Okay.
You find it an issue, I guess.
So just to repeat the question to be recorded. The question is, actually we're using middleware in Swift to send out notifications to RabbitMQ, and what happens if, for example, the message queue is full or RabbitMQ is not available? Shall I? Or?
You can.
Okay. So in this case, there's another background process that ensures that every object that was sent some time ago it actually really has an entry in the database and, tables. So that will take some time. Actually, so far as I know, there were no real problems using this approach. But just to be sure that everything is running fine, there's a periodic job on the user's container. So every user has its own container, and checking if the last timestamp of the container matches with what we got recorded in the databases, actually. And if there's a mismatch, then just using the list command to see, okay, what is here and what do we have in the database. Yeah. Kind of that, yeah. Yeah.
So you are using Swift, you are using Swift, it's okay. How about if you are using C, can you compare?
You mean Ceph? Ceph?
Yes.
So with Ceph, so yeah. In this case, it was very important for us to reuse the existing storage system. And Swift offered a little bit more flexibility in this case. And what is even more important in this case is that we have the Swift proxy, which allows us to run customized middlewares. So when you look at the source code of the Swift proxy server, it's written in Python. Ceph, and especially in this case, it's the Rados gateway, is, as far as I remember, written in C++. So if you have your developers already using Python for other stuff and not working on C++, it's much easier, or it was in this case much easier for them to adopt this, this use case. Yeah.
Great.
All right. No more questions? Thanks for attending this talk.
Thank you, everyone.